Pleasant good day to the conference chair, fellow presenters, and guests. My name is Nishkal George, and I will be presenting a summary of a study entitled Design Complexity as a Driver for Additive Manufacturing Process Improvement, co-authored by Professor Bopana Chowdary. It's a simply formatted presentation highlighting the key areas of this study. A short introduction to the complexity definition is done first. The results are subcategorized as design exploration and design optimization. And before I conclude, I will address the managerial implications of the findings. Product design is the process of imagining, creating, and iterating products that solve users' problems. A key word in this definition is iterating. Additive manufacturing has enhanced the way we iterate designs before settling on design specifications. One aspect of design that additive manufacturing has encouraged is geometric complexity. However, recent studies have been questioning what kind of cost impact exists and how to determine what kind of cost trajectory your design is on, as shown in Figure 1. Two recent studies have attempted to analyze the complexity cost of 3D models. In a study by Pradal et al. In 2017, the researchers used a ratio of surface area to the design envelope volume, shown in Figure 2. Another described in Ferrer et al. 2018 used part volume to envelope volume, which is a similar concept. Both of these studies were able to conclude that controlling design complexity was useful to control costs, especially when iterating conceptual designs. However, these studies did not thoroughly explore the design options or attempt to optimize them for any other manufacturing criteria. Optimization is a critical accelerator in the ability to control and make better decisions in manufacturing. We can optimize design complexity to, for example, stay within production timeframes, simplify assemblies, or even improve quality, as I will demonstrate. This is how we utilize complexity as a design tool to achieve design for manufacturing. The objectives of this study was to utilize design complexity as an additive manufacturing performance indicator to explore the effects of complex design features on manufacturing and optimize design features to achieve target performance and manufacturability for additive manufacturing. In this case, we want a traditionally manufactured product which can be converted to an additively manufactured product with this criteria. In this case, we opted for an automotive air filter. For the method, we begin with a conceptual design with a wide range of possible specifications that we introduce into the experimental model. Model these experiments in CAD, prototype and analyze the manufactured design. Then we can analyze the manufacturing responses based on the complexity of the model and let an algorithm select the optimal design. If the best design the method can produce still does not meet the production criteria, we can revisit the conceptual design. For this experimental model, I used a face-centered central composite design because it was easy to manage the number of experiments. And for my manufacturability responses, I borrowed a complexity index from Pradal 2017, used the actual build time for each 3D print, and used a measure of deviation from the specified CAD dimensions in the z-axis as a measure of accuracy. Our model was given 5 design features with a range indicated by the low and high levels. The design features selected from the air filter model included the wall thickness, shown in Figure 7 by symbol X1, the number of ribs, shown as X2, external fillet, shown as X3, internal fillet, shown as X4, and rib height, shown as X5. Our job is to find the most complex design inside of this search space that still meets manufacturing criteria. Figure 8 shows an example of the kind of differences existing in the search space. Figure 9 gives a macro look at the complexity observed for 32 experimental models. As we can observe in Figure 9, the design complexity for each experimental model varies quite significantly. We have a maximum complexity of about 0.3, which you can compare to Figure 8b, which is a high complexity model. And we have a minimum complexity of about 0.21, which we can compare to Figure 8a, which is a low complexity model. So our optimal design complexity should fall somewhere between the low complexity model and the high complexity model. The main effects plots as shown in Figure 10, provided a preliminary assessment on the influence of independent design features on complexity index and build time. X1, X2, and X5 gave the largest effect on complexity, whereas X3 and X4 did not. As we can see in Figure 10a, there are also design complexity increasing features and design complexity reducing features. X1 and X2 increase design complexity significantly when the highest level is applied. X5 increases design complexity to a lesser extent, whereas X3 and X4 both decrease design complexity when the highest level of this feature is applied. The main effects for build time, as shown in Figure 10b, have larger differences in the way that the design features affect build time. X1 seems to have the largest effect when the highest level is applied, whereas X2 and X5 both have increasing effects, though to a lesser extent. However, X3 and X4 have the highest effect on build time when the middle or center point value is applied. For the optimization, I utilized the MINITAB response optimizer, which was fed our feature boundaries and constraints. It was able to provide optimal specifications for all three manufacturing responses. After manufacturing this design, the model was confirmed to be made in 10% less time than a counterpart of equal mass, and met the 60-minute production time target. It also had an improved accuracy over the average model. So what are the implications? Well, the current product design and development framework suffers from a lack of feedback from areas like quality control and production time. No production planning consideration is really done by the designer. Now, if we take a closer look at Figure 14, which is the current educational PDD methodology, we can see that the design process and the manufacturing process are fundamentally disconnected. Computer-aided design stage is connected to the computer-aided manufacturing stage through the handoff of an STL file. Now, all AM process planning is typically done through AM parameter setup, which are the parameters used to determine how the machine behaves, which creates quality control issues. None of these issues are typically relayed to the designer. The inclusion of design complexity optimization solves these issues by adding manufacturing response feedback, such as quality and production time. And it allows designers to consider production constraints so that no reprogramming of 3D printing parameters need to be done, which is very time consuming. In conclusion, we achieved the initial challenge of obtaining target manufacturability for a case product. All responses were optimized to meet DFM targets. The method improves on those proposed in earlier studies by quantifying and controlling design features. Future work should include creating a method for identification of the most critical design features and expanding this method into other AM products to illustrate this design feature selection. And with that, I thank you for your time, and I hope you enjoyed this brief presentation.